So next up is Fenry Ewing. Uh,
Hello.
Hello. Here to talk about Monte Carlo. Also, yeah, and just product, game, narrative designer from San Francisco. And you were the designer and developer on Firewatch, which is a game I love, and the creative director of NeoCab, which, again, just fantastic, and design lead on Cat Burglar for Netflix. So, quite an interesting CV.
Thanks. Yeah. Hopefully, this will be a little bit more softball than some of the super math heavy ones, because yeah, I'm primarily a game designer and narrative designer, and yeah, a big goal for this talk would be to demystify Monte Carlo simulations for non-statisticians.
Excellent.
Yeah.
All right, well then, go for it.
All right. Yeah. So this is A Million Little Players, practical Monte Carlo simulations for game designers. Um, let's see here. Cool. So yeah, I'm Fenry Ewing. You may have known me as Patrick Ewing. I changed my name recently. Hi. Uh, these are three games that I worked on in a design capacity: Firewatch, NeoCab, and most recently Cat Burglar for Netflix. And on two of the three of these, I got to use Monte Carlo simulation. So I kind of want to tell my story with how I found the need for them and how I familiarized myself with concepts. And by the end of it, you may not know all of the equations for every different type of Monte Carlo simulation, but hopefully you'll have a really good grasp of the concepts and be able to, use them in your own game design, in your own capacity as a game designer. So, brief rundown of the talk. We're going to go through Monte Carlo in a nutshell. I'm going to just do a little fun history of the Monte Carlo method. We're going to try to demystify the specifics of the process, break it down into steps. I'm going to give three use cases from my experience where I use Monte Carlo and what I learned from each one, and maybe briefly touch on how you can use, what takeaways there are, and how you could use this yourself. And then if there's any time left over, we'll do a Q&A. Okay, so what is the Monte Carlo method? When I first heard of this, it kind of sounded like a fad diet, uh, or yeah, like some way to win at cards. But it's actually like a broadly useful, almost, if you've been game designing for a while, it may almost seem kind of obvious, but surprisingly deep method for making predictions about complex systems. It's useful for all sorts of things. And but I'm most interested today in talking about how it's useful for game designs. So let's talk about what it actually is. So at its most basic, you're going to be modeling a complex system, uh, and then sampling it thousands and thousands and thousands of times, with RNG and with like weighted random variables. Um, I'll get, I'll come back to what I mean when I say modeling, and also what I mean by random sampling, because there's definitely pitfalls on all sides. But first, let's go into the history of the method, because I do think it's fascinating. It's great to know where this stuff comes from. Um, so the Monte Carlo method was first used as part of the Manhattan Project to develop the atomic bomb. Obviously, this has murdered a lot of people and is widely considered to have been a bad idea. Um, Essentially, von Neumann, Ulam, and Metropolis were three scientists working in Los Alamos, and they wanted to model what would happen in a chain reaction to enriched uranium. And as you could imagine, they couldn't really afford to just like test this out in a laboratory, because they might blow up all of New Mexico or worse. So they needed a way to mathematically predict this really, really complex system that nobody understood before. Um, so they developed the Monte Carlo system. So why would this be useful to you? You're not a war criminal. You're not a nuclear physicist. Well, I get it. You just want to make games. Well, that's kind of one interesting wrinkle here, is that the whole concept was actually the product originally of one of these three scientists nerding out about game design. So before Alamos, when Stanislaw Ulam was an associate professor of mathematics at the University of Southern California, he got seriously sick. He was bedridden after like emergency brain surgery, and there was like a long recovery period. And during this time, he was playing tons and tons of solitaire. And at some point, he kept finding himself losing. And he's a math nerd. He's like actually one of the best mathematical minds on the planet. And he started asking himself, like, what are the odds of drawing a perfect initial hand here, like a kind of an auto solve solitaire hand? Let me calculate the probabilities. And but he actually surprised himself to find out that it was too complex. His methods that he knew for calculating probabilities, combinatorics and whatnot, were not yielding an answer. So he said, okay, well, what if I just like play this out? Like, what if I just keep playing solitaire or just keep dealing that initial hand? And, I can just wait until I find a winning one and then divide by the number of times I tried, right? Basic, simple. But like hundreds of hands in, he wasn't finding the answer he sought. It was like too unlikely. So he was like, well, this method would work and I can figure out the math, but it's just not practical for a human to run this many simulations unless, girl, can I borrow your computer? There were like definitely less than 10 programmable electronic computers on the planet at this point. But Ulam was buddies with John von Neumann and basically said, can I use your ENIAC? This is an ENIAC here with two programmers, Marlon Westkoff and Ruth Lichterman. And basically said, can you run this like solitaire sim on your computer? And von Neumann is like, oh, that's interesting. And basically, even though this was, incredibly slow machine, both to program and to process, compared to anything we've known, this was the 1940s after all, something that would have taken a normal human years to process, it could run in a couple of hours. And so this was sort of the formation of the technique. You could think of it in that sense as like sort of it's always been a brute force, let's throw processing power at it technique. But years later, they'd used the same basic concept in the Manhattan Project. So this little like throwaway solitaire question ended up like contributing to the atom bomb. Weird. Okay, so let's go back to Monte Carlo in a nutshell, what it is. Well, first of all, I should note, Ulam did end up naming it after this casino in Monte Carlo. I guess his dad used to gamble there. It's called Monte Carlo. It's in Monaco, I believe. And so the basic idea is it's repeated random sampling of a model or simulation. And it's used in like optimization problems. It's like heavily used in computer graphics, like ray tracing and stuff like that. It's used in designing AIs. But for us, I'm most interested in like probability ranges for game design. The basic idea is you're using a lot of randomness to solve problems that might in principle be deterministic, but are too complex for you to like sort of solve in a combinatorics way. Okay, so let's demystify this further if I haven't already put you off. The core, it's basically, this is statistics, it's inferential statistics. You're trying to make predictions. And the two core components are the population and the sample. So let's talk about pachinko. I love this. Sorry, my kid is sick and is screaming in the background. We've got every pachinko machine ever of a given type ever made, let's say, that's our sample, and every ball ever dropped into it. Sorry, that's our population. The sample would be, let's take one of these machines or 10 of these machines, drop 1,000 balls into it in random or like realistic spots where a real player would, and then observe what we get. And the basic, like the way that this works, that you can then make an inference about all of the machines of this type, is that a random sample tends to exhibit the same properties as the population from which it's drawn, right? Basic stuff. It's basic statistics, okay? But you do need your model to be fairly accurate. Like you don't want to get too small of a sample size. Like if you had a busted pachinko machine, it would give you bad results. And you want your sampling to be truly random. If you only drop your balls like right in the middle, that wouldn't be an accurate representation of actual players. Ditto for if you only dropped it in everywhere evenly, right? Okay, so now to some personal examples where I, a non-mathematician, non-statistician, used Monte Carlo for game design. So the first case study, my baby's first Monte Carlo, was when I was approached by a tabletop designer who was about to package up the classic deduction, bluffing, hidden role game Werewolf, which you may also know as Mafia. And this is a folk game that was invented at the University of Moscow in the late 80s. It sort of spread organically through the world. And so as a result, there is no rule book. There's no, here's the best way to play. Here's the way to introduce it to your group, etc. So he had the question here, if he's going to try to be making this package, like he wanted to know things like, basically like, how do we get the best version of Werewolf and introduce it to total noobs? Like basically, how do you generalize the rules of Werewolf to work for every possible group? So like for Werewolf, if you're not familiar with it, or Mafia, there's villagers and wolves. There tends to be fewer wolves and villagers. And then there's also extra rules that make the game a lot spicier and more strategic. So like a seer role who gets to, at the nighttime phase, ask a sort of secret question to find out the true identity of anyone there, unbeknownst to no one. A healer role who every night can pick somebody as protected. So if they would otherwise be killed that night, they survive. So, and then people play Werewolf as few as like 5 people, but you can also play this game with like 20 or 30 people. And at the time I was playing it a lot at conferences. So the question was, how do you balance Werewolf for all different combinations of the roles and all different player group sizes? So I was like, I have no idea how to answer this question. And then I had a friend, Fred Benenson, who is a data scientist at Kickstarter, who told me about Monte Carlo simulations, and we worked together to build one of Werewolf. The code is all on GitHub if you want to see it later, but I'll give you a quick rundown. So basically, the process we followed was you code up a super basic model of a Werewolf game. You pick ranges or weightings for the core variables, and then you're going to randomize within that. You run that model thousands of times with every possible input value for the free variables, weighted by what you think is most realistic. You record the results, then you can sum them by input type. So you record all the results and you can slice that data up and look at it different ways. And then in our case, what we did was you created an interactive rules document. I wish I could show it now, but unfortunately it's no longer online. But essentially it was like the rules of Werewolf, but then you could just live change how many players I'm playing with, how many do I want to seer, do I want a healer, etc. And then it would tell you, here's how many wolves you want. Here's basically like it would give you the winning probabilities based on that. And we found it. Okay, we found it very helpful actually. So just a little bit of code just to show you how basic my very first Monte Carlo was. Basically, you get a stochastic player. You get a sort of representative of a player. In this case, it was simple, like, are they a werewolf or a villager? Are they a seer or a healer? That's all you needed to know. This is one little piece of the actual model, but the things we modeled were the game round sequence. So you have a series of rounds that all play out a certain way, and then at the end of each round, you check if the game's over or not. Day-night cycle, there's a day behavior and a night behavior. Here you can see this is the night phase. We had to code in the end conditions, like the game ends when either all the werewolves have been found or all the villagers have been killed. And we also included some super basic player behavior. So here, we said, well, if you're going to have the seer, their whole goal is I'll randomly look at one of the people, one of the players, and then the game model will tell the seer, yes, this is a werewolf or no. And basically, we could then model like, okay, well, if the seer does discover this, they would share their behavior, and then there'd be some percentage chance that the group actually listens to the seer and kills them. So it has that sort of effect. So we modeled a little bit of player behavior, but you can notice like this does not represent the whole game of Werewolf. Like we didn't factor in player skill. We didn't factor in any sort of human psychology. We didn't factor in, the way that people accidentally give away their roles, etc. But we did learn quite a lot. We got results for real world werewolf play. I should really dig up that page off archive and repost it, because I found it very, very useful. And you just discover things you didn't know, like adding the seer could boost the chances of the villagers winning in some scenarios for 25-30% more. So we did learn a lot, I think, about Werewolf that was kind of hidden. Every time you change these variables, you kind of see a surprising result. But we could have included more roles, and we certainly could have modeled things more accurately. Like there was a lot of hand waviness and fudging. So quick little funny pettiness interlude. I'll be really quick about this. But again, so I'm just a designer and programmer. I'm not a mathematician. And yet when I posted this like rando on Twitter kind of stepped in and sort of said, why are you simulating this? Why don't you use analytical math? And this rando was sort of like, saying, instead of, he says here, instead of throwing darts, better to measure the dartboard. And I'm just getting like, I'm like, who is this guy? And then it turns out he's like a distinguished comp sci professor at MIT. Oops. But I thought it was kind of interesting. I mean, he had published a paper on werewolf probabilities. And I was like, okay, I'm curious. How did you model the seer? This was the most complicated part of our model. Most people playing werewolf model the seer. How did you model this using combinatorics? And he's like, well, I ignored it completely. So I thought that was interesting, and I think that he was opposed to my approach because it was it's less elegant than using pure math. But I just want to note, like, Werewolf is a complex game, and this is the actual diagram of the control flow for the original Monte Carlo Los Alamos experiment. Like, these things are complicated. The systems are complicated, and that's why you can't just ignore variables. Okay, case study number 2, Cat Burglar. This was a Netflix interactive show, so it was something you'd play with from home. You could use your PS4 controller, you could use your remote control, you could play it on your iPad, etc. And it was this like interesting experimental cartoon trivia show. I'll show you a bit of the trailer. Ooh, that's loud.
Tomorrow is the unveiling of the most valuable painting ever. Protect that painting as if your life depended on it.
I see everything.
Okay, I'm gonna stop it there. So, okay, let's just skip to the next one. Okay, so that's Cat Burglar. This was great because this was my chance to use Monte Carlo with actual research data and actual data scientists, thanks to the awesome Netflix research team and our partners there. The basic idea of Cat Burglar is you have a very short period of time to answer these either or questions. They always appear in groups of 3, and you have to get all of them right within a very short time period to move on. If you fail even one or run out of time, you lose a life, and you can potentially, you can get a game over, and then you have to start again. And every time you play, you get randomized questions and a randomized sequence of these like animated predicaments, basically. If you win the question, the Cat Burglar like wins in a funny way, and if you lose the question, he dies in a very funny and gruesome way. Okay, so this was something we'd never really done before as a team. Like, Netflix Interactive had only done Black Mirror and those sorts of branching narrative shows. And so it was like kind of the most game-like thing that had been done at the time. And we had very specific wants and goals. Like, we want the game to feel hard. Charlie Booker, the Black Mirror creator, was very specific. Like, it's a classic cartoon. It should feel hard like a classic Nintendo game. But we also knew that trivia can feel very unfair if you just don't know it. And if it was punishingly hard, we expected you'd see fall off after the first episode. And that's not what Netflix is very metrics driven and really wants to get at least 2 or 3 playthroughs out of you so you can actually see all this great randomized animated content and hilarious trivia content. So we had all these open questions, like, how hard should the game feel? How much time do we give the players to answer these 3 questions? And is it the same on a TV with a remote or versus an iPad? How do we sequence questions? Do we do it by difficulty? How many lives should the player get? How long should the play experience be? And based on their amount of failure and retry and the length, like how much animation and trivia content do we need? Because this stuff is like very expensive. This was like very high quality animation from the like BoJack Horseman creative team. So what did we do? We wrote a small set of test trivia questions. We put them in front of 5,000 US adults. I think we did 25 per participant in a very winnowed down version of the experience, like a glorified Survey Monkey sort of thing. And then we measured their success on each one. Here's an example of like a super early prototype. We didn't have animation yet, so to see how distracting it would be, we used Wile E. Coyote stuff for our internal test. And yeah, you get the idea. So we would crunch all these, we'd record how all these adults did on the test questions, and then we would find a lot of useful data. So here is a graph of the probability of answering all three answer pairs correctly. Each one of these at the bottom is one of these like triple question sets, and you can see the hardest is on the left and the easiest is on the right. And this is just one round of questions. There's hundreds of questions in the actual game. You can see we rate, we go from down like below like basically 12% to almost 90%. So that was useful, and it let us, because we'd actually put the question of real people, we could go into our Monte Carlo simulation, which is coming later, with really solid data on how hard these questions are, as well as data on our actual players. So for one thing, we were able to group questions into 6 different difficulty brackets and use those. Cable is loose. Oh, I'm sorry. God, I just saw my
No, you're good. It's not that bad. It's just like a little hit and miss. So just if there's anything.
I see. I can really quickly change off of my AirPods. I bet it's that to use the camera audio. Let me just try it real quick.
Yeah, I think we have time to do that, especially this is the last talk of the blog, so I could give you a minute or two.
Is that good?
I think it's a bit quiet, but if you speak up,
yeah. Okay, is that better?
I think that's better. Yeah. Okay. Just
cool.
Yell.
All right, I'm just gonna scream my head up. No, thank you for letting me know. Okay, so we were able to like make these difficulty brackets. Another thing we learned was there was a learning effect in the game that we could model. So what you see here is these are the number of playthroughs, basically the number of times that these test subjects had played through the trivia questions. And then you can see that as they go, their success rate rises in a pretty predictable fashion. So like at the beginning, they're just understanding how does this triple question trivia thing work. And by the end, they're just kind of like very gradually improving their reaction time. So that's something we could put, again, these are the sorts of like ranges and weighted random stuff that makes a really good Monte Carlo simulation. So this is like the result. We then like modeled the game in Python code. We used the learning effect estimation, that curve. We used the knowledge of different trivia difficulties, and we then were able to say, how should this experience feel? Well, we are able to tune it to a very specific experience. Basically, we were able to say, we want the game to feel punishingly hard on the very first playthrough. That's what this this red kind of gradient line on the left side here, the horizontal line. Red is the hardest, pink is the easiest. And we're able to like custom order the questions while they're still being randomized within that bracket. We're able to start you off with what feels very punishingly hard, but then adjusting for the learning effect. And we're able to make the game feel gradually easier as you continue to play. If this is confusing, I apologize. I'll be in a breakout room afterward to talk about it. But without the Monte Carlo method, this would have all been guesswork. Even with the original random trials, we had no idea how to sequence them without running thousands and thousands of these simulated games using real data and learning how to sequence things. Okay, next section. Okay, NeoCab. This is like the last example, and it's kind of closest to my heart. I was the team leading creative director here, and neither I nor anyone on the team had really made anything like this game before. In part because it is a visual novel, but it also has a really unique in-game economy, and we weren't really sure at first how to balance it or even what balanced would mean. So a quick rundown of the variables. There was the driver rating. This is kind of the core of the NeoCab economy. You can get fired if you have less than 5 stars for too long, and every time you meet an NPC you picked up in your cab, they give you a rating based on your choices. And so it puts a lot of pressure onto like sort of pleasing people, and it could actually lead to a game over state in a narrative game, which is can be horrible, right? If you have to, no one wants to start over a story from the beginning. Then there's the feel grid. This is our emotional state indicator. Again, like driver rating, it's affected by every choice in the story, and they kind of feed into each other because a low emotional state can lead you to pissing off customers. Pissing off customers can lead to a bad rating, you know? So these things are all sort of like tied together in a complex loop. We had coin, which was a cryptocurrency that you were forced to use in our dark dystopian future. And you use this to pay for fuel. You use this to pay for a place to sleep at night. And you made it through every ride and through side hustles and such. Notable here is that if you ever ran out of fuel and money at the same time, this would be a game over state, literally stuck, because you can't even drive to a gas station to get more fuel, and you can't pick up a passenger to get more money. So we knew that this was a problem we had created for ourselves, and we didn't know how to fix it. So enter Monte Carlo. And one of the real beauties here was the entire NeoCab game design was written in a narrative language called Ink by Inkle Studios, which I highly recommend checking out. And so even though the game was made in Unity, the narrative engine was this tiny little coded language written in Ink. And this let us run the game essentially from the command line and do a Monte Carlo simulation instead of building a model of our game, we kind of already had one and could drive it in a very limited way, or I should say like a very quick and fast way from outside. So this is like a super simple bit of code for choose a random choice every time you hit one. This is like driving the story from outside. This is recording our data. So every time at the end of a run, like we could basically play our game thousands of times with a little JavaScript runner. And then at the end, these are our core variables we care about. We spit them out. We record what the inputs were we were playing with. And then we can slice that data. This is like a little piece of what we did, but basically get metagame reports, like how many people were able to successfully finish the game, this set of runs, like how many, when people finished, when they got a game over, how often was it due to running out of fuel? How often was it due to running out of money, et cetera? And this meant that we could tune these core variables that we had otherwise would be way too terrified to change, like the cost of fuel. How much money does the player start with? How much fuel is used per mile of travel? The rules around when you get fired for low rating, all that stuff. We're able to tweak it with confidence to achieve a desired experience without breaking our game. So these are my takeaways. I know I can see I'm running out of time. First, you have to know your desired player experience. So for Werewolf, we knew we want the game to be evenly balanced. On Cat Burglar, we wanted a game that feels really hard, but also makes you feel like a winner very quickly. It doesn't keep punishing you. It rewards repeated play and feels fair. And NeoCab, we wanted an in-game economy that always made you feel like you were about to lose, because Lena is like a gig worker in a dystopian world. Always felt like you were about to run out of money, about to run out of fuel, about to get fired, but almost never completely runs aground, because that's not fun. So we wanted to create the feeling of precarity without necessarily making that the most likely case. So that's my first piece of advice. You got to first decide what you're designing for, and then Monte Carlo can actually help you achieve that before you launch and put real players in front of it. Second takeaway, use real world data, but you can use guesses in a pinch. In our werewolf sim, we had to guess at how the seer behavior would work, but in my opinion, that's better than just ignoring it entirely. But if you can, do play tests, measure what people actually do, and use informed guesses and informed ranges. Don't just randomly treat every free variable as equally likely as every other one, because that's obviously not realistic. And my last piece of advice is use the latest tools to guide you. I really wish I'd had tools like Machinations when I was starting all this. This is a product I found recently that basically combines into one designing something like a Monte Carlo simulation. This is a sim of dice throw accuracy, but you can actually watch it play out, watch the sources and sinks, and run it hundreds, thousands of times, and you get the graphing tool all in one. So if I was doing a Monte Carlo simulation for game design today, this might be something I would choose. And that's all I got. I'll be in the breakout room since I might be out of time now. But for anyone who wants to talk about game design using Monte Carlo, I'll see you in Rogue, I think.
Yeah, that is correct. Rogue will be the room for you. And yeah, I know that we kind of lost a minute or two fixing the audio, though that was good because it was much better after. I think the one thing that I'd be curious to ask would be, are there some particular kind of traits of a game that lend themselves well to being something you could do Monte Carlo for? Like, for example, one that comes to mind to me is probably limited player actions. If there's only so many things a player can do, versus if there's it seems like the more player actions there could be, the more complicated it's going to get to try and Monte Carlo it.
Absolutely. Yeah, that's a great point. You can do it. There's now people who model Magic the Gathering in Monte Carlo, which is, it boggles the mind to me that that's possible. But Wizards has so much money riding on this and does continually release broken cards. You could make the argument they should be doing this instead of just designing their best. Yeah, I would say the worst one, the player psychology. That's something where I'm like, if you don't run real people through it, and lots of them, thousands of them, that's just guesswork. So, yeah.
Yeah. No, I love that, and I think it great talk. I think too, even just little side things in there. I know it clicked for me of even just how useful it was for you with NeoCap, that you could kind of output part of the generation of okay, this layer into something that you could analyze. That's also just such a great takeaway of so many different analysis, even the expressive range stuff we were just talking about. You can do so much more of that if you can get kind of halfway reports from your game and do stuff with the data.
Totally. Yeah. It was great.
Yeah. Well, excellent. This ended up being quite a nicely, everything feeding into each other's slot. So thank you so much, Fenry. And yeah, hopefully people can go ask some questions in Rogue.